Hello. This video talks about Huffman coding, which is a component of information theory. So, what is information theory? It is a study of the quantization, storage, and communication of information. In our digital world, we know that information is represented in bits of either zeros or ones. So let's say we have four symbols labeled as A, B, C, and D. We can represent those symbols using 2 bits, giving us 4 combinations of bits. So 0, 0, 0, 1, 1, 0, and 1, 1. The average code length for this representation is 2 bits. But is this the best that we can do? To answer this question, we need to talk about another concept called entropy. Entropy is the measure of the randomness or uncertainty of something. So let's say you're in Canada, but you don't know which province you're in. If somebody tells you that you are currently in Canada, this is not information to you because you're already certain of that. If somebody tells you that you are in Ontario, that is information to you because you were uncertain of it before. We can measure entropy using this equation, where H is entropy, and it is the sum of the probability for each symbol times the log 2 of that probability. Entropy gives us the minimum length of code that can be used to represent the set of symbols that we are looking at. This leads us to the main topic of this video. Huffman coding is a method of lossless data compression in information theory. Essentially, it is a greedy algorithm that takes the symbols with the lowest probabilities and then combines them, forming a tree. Let's try to do a simple example. We have the following symbol probability table. There are 3 symbols, A, B, and C, each with their own probability. First thing we want to know is the entropy. Secondly, we want to know what the Huffman code is for this symbol probability table. And finally, we want to calculate the average code length for the code. Let's start with the first question. To find the entropy, we need to use the equation that we talked about previously. Here, n equals to 3 because we have 3 symbols. Now we plug the values into the entropy equation, and we would get h equals negative 0.75 times the log 2 of 0.75 minus 0.1875 times the log 2 of 0.1875 minus 0.0625 times the log 2 of 0.0625. Plugging this into a calculator, we would get that the entropy is equal to 1.014. Let's move on to the next question. Let's start by creating nodes for the 3 symbols with their corresponding probabilities. Next, we have to sort these nodes from highest probability to lowest probability. In this example, they are already sorted in that way. Now we take the 2 nodes with the lowest probabilities. In this case, it's B and C. So we move these 2 nodes to the base of the tree while adding another node in order to combine these 2. Now we add a new branch from B to the new node labeled 0, and another branch from C to the new node labeled 1. Then we add the 2 probabilities of B and C to form the new probability for the new node. In this case, it's 0.25. Now again, we take the 2 nodes with the lowest probabilities. In this case, it's A and the 0.25 node. So now we'll move A to the base of the tree while adding another new node to combine the 0.25 node with A. We now add a branch from A to the new node, labeled 0, and another branch from the 0.25 node to the new node, labeled 1. Now we add the two probabilities of A and the 0.25 node to get the probability of the new node, which would be 1.0. Since this final node is the root of the tree, I'm going to change the color of the node to red. We're ready to find the Huffman code for the three symbols A, B, and C. Let's just start with A. First, we go from the red node and try to find a path towards A. In this case, we simply follow the branch labeled 0, and then we've already reached A. So the code for A is just 0. Next, we'll find the Huffman code for B. Starting again from the red node, we will try to find a path towards B. In this case, we first follow the branch that says 1, and then the branch that says 0, in order to reach B. So the code for B is then 1, 0. Lastly, we have to find the Huffman code for C. Again, starting from the red node, we take the branch that says 1, and then another branch that says 1 again. The code for C is then 1, 1. We've now found the Huffman code for the symbols A, B, and C. We can go on to the next question now, which is to find the average code length. Let's remove the tree and bring back the symbol probability table. To find the average code length is simply the weighted average for all of the symbols. This is the equation we'll be using to find the average code length. You can see it's simply the sum of the probability times the length for each symbol. Again, n equals to 3. And when we fill in the values for L, we get the following equation. Subbing this into a calculator, we will get L equals 1.25. We can now compare this with the entropy that we found earlier. We can see that the average code length is a little bit higher than the entropy. Let's try something else now. What if we group the symbols together? We have our original symbol probability table here. In order to group the symbols into groups of 2, we do AA, AB, AC, and so on. Here is the resulting symbol probability table. In order to find the probabilities for each of these grouped symbols, we simply multiply the two individual symbols together. So for AA, we do 3/4 times 3/4. Now try to find the Huffman code for the new grouped symbols. Again, we create nodes for each of the symbols with their corresponding probabilities. We then sort these symbols from highest to lowest probability. Then we take the two nodes that have the two lowest probabilities. In this case, it's CB and CC. They simply follow the previous steps that we took to develop the Huffman code tree. I'm going to leave this exercise to the viewer. Here's the resulting Huffman code tree that I got for the group symbols. You can also see the Huffman code for each of the symbols in the bottom right corner. Let's now try to find the average code length for the group symbols. To do this, we need to look at the symbol probability table. Again, we use the previous equation for average code length. Here, n equals 9 because we have 9 symbols. When we calculate the average code length, we get 2.07. However, since each symbol is made up of 2 individual symbols, we divide the code length by 2, resulting in 1.035 as our average code length. This value is much closer to the entropy than the previous code length of 1.25. Here we can see that if we group the symbols together, we'll actually improve the average code length. That's all for today. Thank you for watching.